and his PhD in engineering sciences from the National University of Cordova, Argentina from 2019. He's currently a postdoctoral fellow at Carleton University, Canada, and serves as an assistant professor of computer science at the National University of Cordova. He has co-authored 14 papers in international journals and over 25 papers presented at leading conferences with a focus on communication protocols for satellite networks. His current research interests include AI-enabled routing and transport solutions for satellite constellations. Pablo.
Thank you. Hello everyone. I hope you enjoyed the lunch. The topic is the role of DTN in HAPS-Enabled satellite mega-constellations. This is a joint work with Juan Freire, Jorge Quieto, Halindia Nikomeroğlu, and Gunesh Karabulkart. I will start with some motivation about the problem we are investigating, some traditional architectures and novel architectures to solve this problem. What are our contributions here? Some simulations we have done, the conclusion, and next steps. So we know there is like a huge bottleneck from space to ground. And this is mainly because we have more and more sensors with higher resolutions on board on these Earth observation satellites. And they are capable of generating much more data than what they are able to download to Earth with the current communication capabilities. Just to put an example, we have here the Copernicus Sentinels satellites that generate over 20,000 gigabytes of new data every day, and they need to download to the ground. Of course, if they are not able to download this data, this prevents the satellites from getting new acquisitions because they have limited memory. So this ends up having a negative effect on the final applications. The way this is currently handled is mainly with radio frequency waves sent from the satellites to the ground stations. When there is a contact opportunity, which are limited, of course, both in data rate and in time. The order of these data rates are in megabits per second. And if there are some weather impairments like rain, this may affect a little the quality of service or the data rates, but not so much. Now they are proposing also to use these free space optical links or laser links between the satellites and these optical ground stations. Now we are talking about gigabits per second or even terabits per second in the near future. The main problem here has to do with the atmosphere. Now that we move to higher frequencies, the atmosphere has a much larger effect. For example, some atmospheric disturbances or some weather impairments. If we have a cloud cover here, this acts as a blockage, so the optical signal cannot pass toward the optical ground station, and this means that the link is not available, right? So we have these disruptions, and I think you may guess what we could use here that we have these disruptions. Now they come to the picture, new kind of nodes. Actually, they are no new nodes. These are very well-known platforms called HAPS, but the way we are using or trying to use them is new or is novel. HAPS means high altitude platform stations. This is a definition of ITU, and it means a station on an object at an altitude of 20 to 50 kilometers. And at a relatively fixed point related to the Earth. The word station there means that there is a payload, right, on this platform at 20 kilometers. And that payload can be a sensor, a radar, an optical camera, or it can be a communication payload. When it is a communication payload, and when this communication payload uses the same frequency spectrum as cellular base stations, in that case receives the name of HIPS. HIPS means a HAPS used as an international mobile telecommunication base station, a cellular base station. And we coined a new term here because we are trying to use these HAPS not as a terrestrial base station, but as a high altitude ground station. So that is what we call HACs. And there are of different kinds. We may have this like Loon from Alphabet. We may have some Zeppelins like the ones proposed by Thales. And also these kind of airplanes or UAVs that use solar panels and that can move or make circles. There are of different kinds, but all of them share this property of being at high altitudes and providing some kind of communication or any other payload. Now, if we considering this kind of new nodes, we can tackle the problem I was mentioning before of cloud blockages when we use free space optical links by putting one of these HACs in between the LEO satellites and the optical ground stations. And there are several benefits here. The main benefit is that this link between the LEO and the HACs, there are no cloud blockages there, right? Because this platform is above the clouds. That is the first advantage. And the second one is that if there are some cloud blockage here, we can send data to the HACs. The HACs can store by using some DTN scheme. And when the cloud blockages is not there anymore, we can effectively perform this transmission toward the Earth. A second advantage is regarding an increasing coverage. Because as you see here, if we have this platform, these HACs above the ground, when the LEO comes here, it will have line of sight before having line of sight with the ground station below. And that means that we can start transmitting data much earlier than if we want to connect directly with the ground station. And this is not minor. It is in the order of 20% improvement in coverage. If we consider a constellation of LEO that are observing Earth, the effect is obviously multiplicative. Now, our contribution here has to do with perform an evaluation and comparison with these two architectures. We have the traditional one, or relatively new, of LEO satellites observing the Earth, making acquisitions, and using many optical ground stations to download this data. They are subject to weather impairments. With this other proposed architecture where we have these HACs in between the LEOs and the optical ground stations. And these HACs have this store, carry, and forward capability. We perform the evaluation in terms of delivery ratio and delivery delay. And we also perform an equivalency analysis where we try to answer the question, if I have one of these HACs, how many ground stations do I need to achieve the same performance? So we perform different simulations by using our platforms called DTN Sim that implements different routing algorithms like CGR and the DTN approach. We consider in terms of the ground stations the location of the very well-known KSAT global network of ground stations. We just consider one LEO satellite that is making this, obtaining these acquisitions, and that needs to download all of this to the ground. There are between 1 and 10 ground stations from this KSAT network. And the other case is, again, one LEO, but we change the number of HACs between 1 and 5, which are about these ground stations. There is some traffic generation over there. And here we have also weather modeling, how we simulate these cloud blockages between the satellites and the ground. Basically, we consider mean values of these two parameters that we call time to cloud cover and time to clear sky. This basically means we first have the link available. We wait for some exponential time, which is this time to cloud cover. After waiting for this time, we have a cloud blockage here. And then we wait for another time call this time to clear sky. After this time, we have the link available again, right? So all of these parameters will vary between these values and follow exponential distributions. This is our results. First, the delivery ratio, which means basically as I generate a given amount of data at the LEO, I need to download this to the ground. What is the percentage I effectively download to the ground after the simulation time? In the horizontal axis, you see this time to cloud cover I was mentioning. If I have shorter values of this time to cloud cover, this means I have more cloud blockages. If I have longer times, it means less cloud blockages. Here, these dark colors are the schemes with the ground stations over here, and the light colors are the schemes with the HAPS. So we are comparing these two schemes. What we see here is that when we have less cloud blockages, all the schemes deliver all the data that they generated. But when we move toward more cloud blockages, we start to see some penalization for the different schemes. Of course, the schemes more penalized are the ones with the less number of ground stations. That is obvious, but what we see here, which is a little surprising, is that the schemes with HAPS are able to deliver all data in every value for this time to cloud cover. Then if we increase this time to cloud cover, we make it a little longer, there may be some benefit for having the ground stations distributed across the Earth. And we see here that we start to see some penalization for the schemes with HAPS, but not so much as the other schemes with only ground stations. If we move to the delivery delay, because this is other important metric, how much time it takes for the data to finally arrive to the destination, because I can send to these HAPS, but maybe there is a cloud blockage for 1 or 2 days, I will have a delay of 1 or 2 days, right? We see here that the situation is a little more complex. So we have many crossing points between these two schemes. And the main takeaway here is that when we have more cloud blockages, the schemes with the HAPS show some advantage. But when we move toward the less cloud blockages, this advantage diminishes a little. For example, we see here some equivalencies. 2 HAPS would be equivalent to 10 ground stations. But if we move toward the right, we see that 1 HAPS would be equivalent to 2 ground stations under some specific weather conditions. Our final results are an equivalency analysis. In this horizontal axis, we have the number of ground stations. In the vertical axis, we have the number of HAPS. And these different colors are different weather conditions in terms of time to cloud cover and time to clear sky. If we are over here, we see this point here, 2 HAPS would be equivalent to 8 ground stations under these weather conditions. If the weather conditions are less favorable, and with less favorable, I mean we have a higher number, a longer time to cloud cover, right? I have longer time to cloud cover. I have less time to cloud cover. I have more cloud blockages. And that means that I go here, right, to a less favorable situation where 2 HAPS would be equivalent to 3 ground stations. So the conclusions are that we evaluated the use of these high altitude ground stations in order to improve the downlink performance of these all optical LEO satellites for Earth observations. This is something I forgot to emphasize. The idea is that these LEOs will have only optical terminals, and that is with the aim to reduce the complexity. We don't have RF and optical, we only have optical. And with this architecture, they will be able to improve the downlink performance at the same time that reducing power consumption and weight. Also, in terms of delivery ratio, even one of these HAPS, according to our comparison, one HAPS would be equivalent to 10 ground stations in terms of delivery ratio. We pay the cost a little with delay. In terms of delay, the scheme with HAPS provides advantages when we have many cloud cover blockages, but of short duration. If these cloud blockages start to be more and longer duration, in that case, these schemes can take more advantage of the geographical distribution of many ground stations and to obtain a better performance. But if we have many cloud blockages of short duration, by using this DTN, store, carry, and forward, optical high data rate links, we can obtain advantages with this architecture. And finally, we obtain all of these metrics with many different weather conditions. What are our next steps? We just considered in the previous analysis only one LEO, HAPS, and optical ground stations. The next step is to have a constellation of LEO satellites communicated with intersatellite links, optical intersatellite links. You see here optical toward another satellite, optical toward the ground. And here there is an interesting situation in the sense that we have a fully connected network here, although with interruption, of course, but fully connected in time. And then a more deterministic connections. But here on the ground, a more stochastic set of connections, because this basically depends on the weather that we cannot predict so well. So the challenges here appear even with CGR, which is very well developed. But in this case, CGR takes this very greedy way of working where it tries to send all the data to the first node that would be able to see and to download to the ground station, maybe subestimating the capacity of this link, right? Because it is not using information about the weather. So all the traffic that comes here, we have two possibilities. Either we wait there by avoiding sending back this to the LEOs, increasing the delivery time, or we allow the possibility to send this back to the constellation, maybe with a chance of creating loops. This would be equivalent to send from a rover on Mars toward a relay, the orbiter, and then going back to the rover to use a direct link to the Earth, right? So we want to avoid that kind of effects when using these schemes. We send this to this conference in Middle East about communications, and we are waiting for the review process. Other items we have in our roadmap are about buffer management. Now we have the buffers of the LEOs, the buffer of the HAPS, and of course we would like to put closer the data toward the Earth, so on the HAPS buffer as soon as possible. But we have this problem of buffer management because both LEOs and these HAPS have limited buffer. So now we are in the process of optimizing delivery time, but also optimizing buffer usage. We want to consider, in addition to delay tolerant traffic, we want to consider delay sensitive traffic, because all of this is also proposed for 3GPP and ITU for 5G, 6G networks. And finally, the challenges that we didn't consider so much in this work, but we have challenges of this LEO in the sense of pointing toward the HAPS, right? We have the LEO moving, the HAPS may have also some movement, and we need to point a very narrow optical beam toward the HAPS as this LEO is moving. Maybe considering these inaccuracies or other impairments that we have in this process could be taken into account in our future work. So I finish with this slide. These concepts of having these platforms in a stratosphere, 20, 50 kilometers, is not new. These Mars robot balloon systems or the Mars aerial platforms were already proposed in the 80s and the 90s. Some feasibility studies were done. Of course, Mars has this more light atmosphere, so it's not so easy as it is in Earth to have these platforms. maybe we should increase the size, or maybe we should have platforms that can be moved by using solar panels. We have here the mission that we heard about this yesterday, about the Dragonfly mission to Titan, the moon of Saturn. We have also this Venus atmospheric platform proposed for the year 2029. And we have here a workshop that was recently developed in Netherlands, HAPS for ESA. So all of this is showing interest in having these platforms in the stratosphere. And our contribution there is to see or to analyze how we can use DTN in order to take advantage of these new kind of nodes, in order to take advantage of all of these new use cases, in order to remove or at least mitigate these blockages or this bottleneck from space toward the Earth. And of course, if we can solve some of these challenges on Earth, then they will be applicable also to these same use cases, but for interplanetary cases, where will we have in the future these platforms at different levels of altitude. That's all. Thank you.
We have time for a couple of questions.
Yes.
I was wondering, in your simulation, what were you modeling in terms of the operational duty cycle of the HAGs? Because when I was on Moon, one of our main constraints was that power really had to be conserved overnight in order to keep the electronics from freezing. So we opted not to operate any of the 3 GPP downlinks, which would basically mean HAGs in the atmosphere on the night cycle, could be basically took offline for communications purposes.
Yes, very good point. We didn't consider any duty cycle in the HAGs. This is part more of the operational challenges that we have. How to provide power, how to keep the altitude or the position, the pointing, everything are challenges that we didn't consider for this study. But yes, we think that still taking into account of all of these things. We have satellites at much higher altitudes, and also with the challenge of radiations, the challenge of power. So we think if we can do it at those altitudes, we can do it a little lower.
And I suppose a related question was, in the situation where you had a LEO platform being able to see more than one HAGS platform, were you also considering the possibility that there could be a HAGS to HAGS mesh?
Yes, that was considered in our group. Actually, the group where I am at Carleton, they have this expertise in this HAPS or HAGS, as we call it now. And they are proposing having inter-HAPS links. So links between the HAPS. It could be optical, it could be RF. They are considering these use cases. Of course, the cost would increase also because we would need to have several HAPS, and the range of these inter-HAPS links should be smaller in range, right? Because they are at 20 kilometers. So we cannot have 2,000 kilometers of range. Yes, I think we can handle something in the order of hundreds, maybe, of kilometers.
Mm-hmm. Any other questions? Well, thank you so much.
Okay, thank you.